Afternoon, we just have our first quiz. If you are a distance student, you have received an email with the instructions from me how to do the quiz in this afternoon or this evening until 12 midnight. You have time to do it. If you have not received any emails from me, that means you are not checking your MSD email account. So please let me know, and I'm going to send you to your other Gmail or whatever email account that you're using. I'm not going to go through the solution of the quiz now because we have distance students online and they haven't taken the quiz yet. So we are going to go and continue the lecture. Hopefully we are going to deal with the solution next time on Thursday. So what we did last time was we looked into that paper. We picked one of those topologies, which is the topology that appears in cell B1. And we looked at the different ways of turning the switches on and off. For instance, the first case that we considered was S2 and S4 are the active switches. By active switch means they are transistors, and that means the gate signal or the command signal or the controller is actually directly controlling them. And under those conditions, we realized that the voltage gain is D over 2D minus 1. Then we looked at another case, and that was S1 and S3 are the active switches, and the gain was 1 minus D over 1 minus 2D. Then we looked at a more general case, and that is the switches are not the switches are simultaneously turned on, but like switch S4 is turned on for a longer time. So technically here we have two different signals for switches S2 and S4. Therefore, I had to define a D2 representing the duty cycle applied to switch number 2, and D4, which was the duty cycle applied to switch number 4. And then we found the voltage gain of this. Now, there is even one more general case that I'm going to talk about today, and that is, okay, let me see if I can copy and paste this. Let me just copy and paste the whole thing. All right, maybe I didn't copy it. Okay. So the more general cases, let's erase this thing. So we are focusing on switches S2 and S4 as our active switches. S2, which is the complement of S1. So this, let's say this is one switching period, kind of a standard, but then for S4, we have a time shift. But still, the switching frequencies are the same. You shouldn't mess with the switching periods or switching frequencies, but they are not turned on at the same time. There is a little bit of a time delay between, a large time delay between the switch command for S2 versus S4. So here you can see you have 4 identifiable modes. Like first, you can realize that both switches are, the top switch is on, the bottom switch is off. Let's call it T1. Then we have both of the switches on. Let's call that time period T2. Then the top switch is off, the bottom switch is on. Let's label this to be T3. And then finally they are both off. All right, so we have these 4 identifiable basically modes. Obviously, I have to also determine D2, which is the duty cycle for switch number 2. So this length is D2 times the period. And also D4 which is the duty cycle associated with switch number 4. All right, so we want to see if we change the switching command to this more generalized case, what would be our voltage gain? So we have 4 modes. We have to look at each individual mode and see what's going on in the system. Like in mode 1, and this is the duration of this mode, and top switch is on, bottom switch is off, and VL turns out to be 0. Okay, so S2 is on, and S3 is also on. So basically, we are kind of shorting VL. Then mode number 2, which is happening in this time interval, and in that time interval, S2 is on and S4 is also on. So if you look at the trick that we were playing last time, the voltage drop across the inductor would be V in minus V out, or the output capacitor's voltage. Then the third mode, the top switch, which is S2, is off. That means S1 is on, and then S4 is on. Okay, in that mode, the voltage applied on the inductor will be Vn, and finally both of the switches are off. S2 and S4 are both off. That means S1 and S3 are shorted, and in that case, the voltage applied across the inductor is actually Vc. All right, so you have to be able to successfully describe the voltage that is applied across the inductor as a function of either 0 or the input voltage or the output capacitor or some sort of a capacitor or a combination of them. All right, under steady state conditions, on average, we should not have any voltage, any DC voltage applied to the inductor. Therefore, the average value of these signals should be 0. That means 0 times T1 plus V in minus Vc times T2 plus V in times T3 plus Vc times T4 should be 0, okay? And we have to do a little bit of a manipulation. You have to remember T1 plus T2 plus T3 plus T4 is T, capital T, which is the period. The other thing is T1 plus T2 is duty cycle number 2 times the period. So that's another equation. And then the third equation is T2 plus T3 is D4 times the period. So if you have these 3 equations in mind, you can actually manipulate this equation and find it like this. Vc over Vn is minus T4 So remember, for instance, if we want to eliminate T4, we can say T4 is nothing but T minus T1 minus T2 minus T3. So kind of combining all these equations, you will end up with something like this. And when we were looking at the last case last time, it was actually giving us the same voltage transfer equation. So the conclusion that we can reach now is if we create a little bit of a phase shift between the command of S2 and the command for S4, the voltage transfer ratio does not really change, which could be good news. But there are converters that actually, if you create a little bit of a phase shift, you're going to actually see a different voltage transfer ratio. So you may ask, okay, if creating this phase shift, which is like labeled T1 over here, doesn't really change anything, why do we have to do it? We don't have to do it, but you may actually look at the pattern or the ripple of the inductor currents and realize actually having this phase shift may actually help you normalize that ripple or make the peak-to-peak ripple a little bit smaller or something like that. So it's actually an extra degree of freedom. It doesn't change your output voltage, but may actually change some other components in the system. So it may actually it might be good to actually use. All right, so this is all about cell number B1. We are going to look at another cell on that paper, which is cell number H2. But we are not going to look at all these different cases, just a very classic case of switches, for instance, S1 and S3 are identically commanded. And then we are going to move on to some other topics. Do we have any questions? All right. So you can see now you should be really good at this. You should actually be able to, as a homework assignment or like, I don't know, future quizzes or qualifying exam problems, things like that, you should be able to, if a DC-DC converter is provided to you, you should be able to identify or find out the voltage transfer ratio of that particular converter.
Dr. Ferdowsi.
Yes.
So, do we get to decide the sequence of the gate pulses and which switches should be complementary and which shouldn't be?
So the question is how do we determine the sequence of the switches, something like that. It's up to you. Like for instance, if your objective is to create a voltage transfer ratio like this, then that means you should actually command S2 and S4. Then if your objective is to create a voltage transfer ratio like this, which is 1 minus D over 1 minus 2D, then your commanding switches or active switches should be S1 and S3. So it's actually it's based on the objective that you are trying to satisfy. All right, any other questions? Okay, so now let's move on to cell H2. Cell H2 is a little bit fancier because it has 2 inductors and 2 capacitors. One of the capacitors is actually the output capacitor. Let me see if I can make it a little bit bigger. All right, so I'm just going to draw this cell over here. So this is H2. And it doesn't matter how you select the polarity. I'm just going to assume that the left one is positive, the right terminal is negative. It doesn't really make a difference. Then in parallel with this inductor, we have a capacitor. Which is labeled C1, and then again I assume this is VC1. It doesn't really matter what your assumption is. VC1 in the end may end up to be negative. That means your original assumption was not correct. Then we have a switch here. Which complements this switch. So this is S2 complementing S1. And in between there is an inductor. And then there is this 4, which complements. This is another switch basically, which complements S3. So this is our output voltage or the voltage across capacitor 2. Again, I don't know what polarity it is. I just assume the top terminal is positive, the bottom terminal is negative. All right, so this is our DC to DC topology. And let's say, once you determine the polarities, later on we are going to talk about them. But anyway, this is IC1. But once you determine the polarity of the voltages, then you have to follow the passive sign convention to determine the direction of the currents. IL2, like in simulation, we are going to look at some of these. IL1, and that's pretty much, okay, IC2. I'm going to label these nodes because I'm going to go through some simulations, so I need to have a label for these nodes. 1, 2, 3, and 4. Okay. So remember the very basic rules of synthesizing converters. We need single pole, double throw switches or complementary switches. And from the throw terminals, you should have a voltage, a stiff voltage. For instance, if you look at S1 and S2, there is a stiff voltage actually connecting these throws to each other, so that's not violated. The other one is the pole current should be a stiff current, and you can see the pole current here is a stiff current, so no violation so far. If you look at S3 and S4, which are also complementary switches, you can see that there is a stiff current going into the pole. And the other thing is the voltage, you can find a path of a stiff voltages connecting the throws. So if this is one of my throws and this is the other throw, let me do a different color. I need to be able to find a path that is only including the stiff voltages to connect them. And actually you can do that. So again, no violations so far. So this is based on our very original rules. Unfortunately, I have to raise this because otherwise the picture is going to get really messy. All right, so hold on. All right, so we got to define the switching pattern. So the part A of the paper, or case 1, is assuming that this is our switching pattern. S1 and S3 are the active switches. And obviously S2 and S4 are the passive switches. So we have only 2 modes, mode 1 and mode 2. All right, so let's look at the system in mode 1. In mode 1, the duration of the mode is from 0 to dt. And I'm just going to write it first and then explain it second. VL1 turns out to be VC1. Because we have 2 inductors, we have to look at both voltages, VL1 and VL2. All right, how do we get these? S1 is on, so I have a short circuit path here, and S3 is on. That means I have a short circuit path basically here. So if you look at VL1, technically it is nothing but VC1, okay? What about VL2? VL2 is, look at this loop. The difference between Vin and VC1 basically. So this is, so at any given mode you have to be able to write the voltage that appears across your inductors as a function of those stiff voltages. So this was all about mode 1. All right, now let's move on to mode 2.
So, Dr. Ferdowsi,
Yes?
according to the polarities assumed of VL1 and VC1,
Okay.
so we write VL2 is Vn minus VC1.
Right.
So, like, both of them have same polarities.
So the question is KVL being violated here?
No. I think it's fine. So.
All right. Okay. All right. So let's look at mode 2. Duration of the mode. Let me write it first. VL1 turns out to be Vn minus VC2. And VL2 turns out to be negative VC1. Okay, now let's take a look and see what's happening. So in mode 2, S1 and S3 are off. That means S2 and S4 are shorted. So if you are looking, for instance, for VL1, look at this loop, which is V in minus VC2. And then if you're looking at VL2, look at this loop, which is the opposite of VC1, basically. Okay? So again, we were successful in describing the inductor voltages in terms of stiff voltages. All right, so we are in business. Now all we have to do is just make sure that on average these voltages are 0, basically, and then find VC1 and VC2. So steady state indicates that both inductor voltages on average should be 0. All right, so that means for VL1, VC1 times dt plus V in minus VC2 times T minus dt should be 0. For the second one, for VL2, that means V in minus VC1 times dt plus negative VC1 times T minus dt should be 0. Okay? So the second equation is very easy because in which we only have VC1 and V in appearing. So you can easily conclude that VC1 is V in times D. All right? Kind of like there is like a buck action going on between the input voltage and VC1. And we need VC1 on the top equation. So now we can actually replace it on the top equation because we need VC1 over here. So if you put it up there and then rearrange things, you're going to realize that VC2 over Vn, which is the overall voltage gain, is 1 minus D plus D squared over 1 minus D. All right, something like this. And the paper actually suggests the same voltage transfer ratio. All right, any questions? All right, so one last try, and that is the same topology, only a different switching scheme. So let me just copy and paste this thing. All right, assuming I selected everything, let's take a look. All right. It's not bad. Okay, so I have to redraw a bunch of stuff. For instance, this thing has been shifted. And this is part 2 or segment 2. This time we are applying the active gates to S2 and S3. All right. Okay. So this is part 2 or case scenario number 2. And now let's take a look. For instance, in mode 1. First, you identify the duration of your mode. VL1 turns out to be VC1, and VL2 turns out to be negative VC1. So why is that? So S2 is on, S3 is on. Okay, S2 is on. Oops. S2 is on, S3 is on. So VL1 is VC1, and VL2 is the opposite of VC1, okay? Negative VC1. All right. Okay, in mode 2, first identify the mode, otherwise you say, oh, I'm going to remember, then you're going to actually get confused. You better write it down. VL1 is Vn minus Vc2, and VL2 is Vn minus Vc1. Now why is that? So S2 and S3 are on, they're off. That means S1 and S4 are on. S1 on. And by the way, we had a switch over here which is missing. Okay, S4. Okay, so this is also on. So if you actually take a look, VL1 is, take a look at this loop. VL1 is Vn minus Vc2. And VL2 is, take a look at this loop. Vn minus Vc1, basically. Okay. So remember, in none of these equations, you should cross a switch that is open. Therefore, the voltage of that switch is going to appear, and we don't really want them to appear, so we should avoid them. Okay. In order to get, okay. Switch back to our original color. Okay, so again, under steady state conditions, these average values should be 0. Okay, so this indicates that Vc1 times dt plus Vn minus Vc2 times t minus dt should be 0. Also, negative Vc1 times dt plus Vn minus Vc1 times t minus dt should be 0. All right, so the second equation is really easy to kind of rearrange, and that is indicating that Vc1 is 1 minus d times Vn. And we need that for the top equation because Vc1 appears on the top equation. So overall, you can conclude that is 1 plus d. Okay, so the output voltage, or Vc2, is always larger than the input voltage, ranging from input voltage all the way up to twice the input voltage, something like that. All right, so this was our last exercise. Now, if you are curious about, for instance, let me just verify these using like simulation tools and stuff like that. You can, for instance, use MATLAB or Simulink or Plex. Plex is easier. You can actually arrange the components, but sometimes it's actually a little bit of fun to actually further investigate the system and see if you can write the equations in the system. So what I'm trying to do is to, for instance, simulate this system in terms of the math that is behind the operation of the system. So this is what I have done, and I'm going to show you how. You can see there is no switches or anything over here. I'm just going to explain how these equations appear. So, so let's take a look. For instance, that's why I'm actually labeling the nodes, like node 1, node 2, 3, 4, and I have to be able to determine each one of these nodes as a function of our switching functions as well as the step voltages. For instance, if you look at node 1, assuming that, for instance, this is our ground node, the voltage of node 1 with respect to the ground is nothing but the input voltage. So let me just draw it over here. The input voltage, okay. Now what about the voltage of node 2? All right. Node 2, there are switches connected to node 2, and assuming, for instance, S4, let me see, S3 is on. Okay, if S3 is on, I'm just trying to make sure I have all the nodes over here. If S3 is on, basically node 2 is nothing but Vin minus VC1, right? Let me write it this way. Okay, and it is VC2 if S3 is off. Okay, so how do I get this? If S3 is off, that means S4 is on. Okay, and if S4 is on, node 2 is shorted to the ground or connected to the ground through capacitor C2, so it's VC2. All right, so I can write it in this way. So mathematically, I can write it in this way. Okay, what are S3 and S4? S3 and S4 are the commands that are applied to the switches. So if the switch is on, S3, for instance, is 1. If S3 is off, if switch 3 is off, S3 is 0, and so on and so forth for S1 and 2 and 4, basically. Or you can rewrite it in this way. I mean, here I'm assuming that S3 is one of the active switches. So if S4 appears, S4 is complementing S3. So I'm just trying to get rid of S4 and replace it with something that is dependent on S3, so which is 1 minus S3. So remember, S3 and S4 are complementing each other. So S3 plus S4 is always 1, and one of them is the opposite of the other. All right. So I have V1, I have V2. So I successfully determine V1, I successfully determine V2, and V1 minus V2 is nothing but the inductor voltage. So technically, you can argue that VL1 is nothing but V1 minus V2, and then you use an integration block to give you IL1. Having the voltages available and having the switching functions available, you can actually construct all the currents of the inductors. So now let's focus, for instance, let's focus on the second inductor. I need the voltage of node 3, and I also need the voltage of node 4. Looking at node 3, I can find a path that goes through node 3 to the ground, which only includes VC1 and the input voltage. So V3 is Vin minus VC1. It is independent on the switches. Okay? What about voltage of node 4? Well, it depends on S1. It is 0 or grounded when S1 is on. You can see that if this switch is on or shorted, then switch 4 is actually, node 4 is grounded is actually grounded, so it's 0. And if S1 is off or S2 is on, then actually node 4 is actually connected to node 1, which is connected to Vn, so it's Vn. All right? So I can write as V4 in this form. Or if you are trying to eliminate S2 as an independent switch and just have all of the active switches involved, which is switch number 1, for instance, here, V4 is 0 times S1 plus Vn times 1 minus S1. So again, S1 and S2 are the commands that are applied to the switches. 1 indicates that the switch is on, 0 indicates that the switch is off. So we have V3, we have V4, and V3 minus V4 is the voltage that applies to inductor number 2. So VL2 is nothing but V3 minus V4. So if I integrate that, I can actually get the inductor current number 2, basically, current of the second inductor. All right, so we assume we have the voltages, we find the currents. Now we can assume we have the currents to find the voltages. For instance, I'm trying to synthesize the current of the first capacitor. All right. So I'm trying to synthesize this current over here. Okay. So this is basically this current, which is IL2 plus this current. And this current is nothing but negative of IL1 times S3. So if S3 is on, basically it is actually equal to the opposite of IL1. So let me write it down there. All right, so the current of the first capacitor is times S3. So remember, these currents should be determined based on inductor currents. So up there we found IL1 and IL2. So for the rest of the equations, you should be able to use them. That's why on the right-hand side of my last equation, only IL1 and IL2 appear, as well as the switching functions. So technically, once I construct this signal, I just integrate it. And that gives me VC1. And remember, when I say integration, that means there is a division by the value of the capacitor or the value of the inductor involved, which I'm not going to draw it over here because the figures are going to get a little bit more complicated. All right, so this was constructing VC1, and up there, wherever we have VC1, we can actually use it. For instance, here I have VC1. So down there, I just constructed VC1, so I can actually feed it back over here. Or I have VC1 here, or that's pretty much it. All right, now what about IC2? The current flowing into the second capacitor, it is actually IL1 times S4 minus VC2 over R. This is the output capacitor. So let's take a look at this. All right, we are trying to identify this current, which is this current minus this current. The right-hand side current is just the output voltage divided by R, easy. And the left side current is the current of switch S4, which is the current of inductor L1 multiplied by the switching function S4. Yes, we have a question.
How come that current is just IL1? You're not factoring in the current of IL2 if switch... Oh, because switch 3 and 4 are complementary.
Yes, switch 3 and 4 are complementary. That's exactly right. So remember, the current of switch 4, so just write it over here to make it less confusing. So let's say this is IL1, right? So this current is always IL1 times S4. And this is IL1 times S3. And they're complementing each other, okay? Good point. All right, so let's go down there and write it. Actually, I already had it written, so let's just continue. Okay. Or let me just rewrite this in this form. Let's say S3 is our active switch, and here S4 appears, so I just, instead of S4, I'm just writing 1 minus S3, yes?
In the second equation for IC1,
Mm-hmm.
why is the IL1 negative? Why did we consider the current is flowing from 3 to 2 and not from 2 to 3?
Oh, you're talking about this negative sign over here?
Yep.
All right, so let's look at the diagram. All right, let's use blue this time. So we are trying to identify this current, which is this current minus this current, right? And the top current is IL1 times S3, okay? Okay, minus VC2 over R. So we got to integrate this. And then this is giving us VC2. Okay? So the first set of equations that I had, first of all, you always have the switch commands, you always have them. They're actually externally applied to your converter. So there's a DSP or an analog controller providing the command to switches S1, S2, S3, and S4, and two of them are complementing the other. The first set of equations that I had, I assumed I have all of the voltages, like V in voltage, V out voltage, VC1, VC2, as many capacitors as you have. And then I found the inductor currents. The second set of equations that I had, I assumed that I have all the currents, which is current of inductor 1 and inductor 2, and then I was able to synthesize all of the voltages, which is voltage of capacitor 1 and capacitor 2. So once you do that, you end up with this file. Let's see if I can make it a little bit smaller so you can see. Zoom in. All right. Actually, you know what? This is too small. Let me just make it large. View, zoom. Oh, no. Okay. So what's happening here is, first of all, I'm determining my load value, which is 5 ohms or 2 ohms. My input voltage is 48 volts. S1 is the switching command to switch number 1, which is basically a signal with an amplitude of 1, the switching frequency of 100 kilohertz. The duty cycle is chosen to be 50%. And S2 is 1 minus S1, basically. It's complementing S1. And then S3 is also another active switch. Amplitude 1, switching frequency is the same, 100 kilohertz. So basically these S1 and S3 are actually exactly identical. I just defined them separately, so in case you don't want them to be identical, you can actually do it. Duty cycle is also 50%. And S4 is basically 1 minus S3. So these blocks on the left-hand side are S1, S2, S3, and S4, in case you need them. Now let's, for instance, look at VL1. Remember, VL1 was V1 minus V2. And V1 was Vn, which we already have, or minus VL2, which is Vn minus VC1 times S3 plus VC2 times S4. So we are actually referring to this equation over here. This equation over Vn minus VC1 times S3 plus VC2 times S4, or 1 minus S3. This is the equation over here. And then once you have VL1 divided by the value of the inductor, which in this case I have assumed is 10 microhenries, and then do the integration, you have IL1. Same thing, for VL2 you synthesize it, divided by the value of the inductor, integration, IL2. And then for the capacitors, you have to synthesize their currents. IC1 is IL2 minus IL1 times S3. Okay, let's take a look. IC1 is IL2 minus IL1 times S3, the equation over here. So this is that equation, and the bottom one is actually the last equation that we have. And these two capacitors, I've assumed they are like 300 microfarads. So this gives us VC1 and VC2. And that's pretty much it. So now you can actually run it and look at a bunch of waveforms. For instance, I'm looking at VC1 and VC2. VC2 is actually your output voltage. I don't have a numerical number in mind, what it should be, but it is actually settling around like 72 volts. So I think if you numerically calculate it with a duty cycle of 0.5, you should actually get to that number. Then if you are curious about like IL1 and IL2, for instance, you're curious to see if this converter is operating under continuous conduction mode or not. You can see they are both running under continuous conduction mode, although the last one, I have to run the simulation for a little bit longer. The top one is definitely doing that. There is a little bit of a ripple in the system. That's because it's a fourth order system. We have two capacitors and two inductors. It actually takes a longer time for the system to settle. And also for the second inductor, we are above zero, so we are good as long as the continuous conduction mode is concerned. If I really want to reach the steady state, I have to run the simulation for a longer time so that for this resonance frequency to be damped down. I don't really know why I'm drawing this figure, but this is, for instance, you're curious about the current waveform of switch number 4. And remember, the current of switch number 4, I drew it up here actually earlier. We had a question about it. Current of switch number 4 is nothing but IL1 times the command that is applied to switch number 4. So I have it here constructed. Current of switch 4 is IL1 times S4. And then we have what it looks like. Again, that ripple is there, and you can see that it is the classic waveform for a switch, for instance. It jumps from 0 to a peak value of I max, then ramps down to I min, then jumps back down to 0. This ramp is not supposed to be there. This is basically because of the time resolution in MATLAB is not small enough or high enough, and this ramp is not supposed to be there. So the ramps are either 0, and this is the declining ramp is because of the value of L2 basically, okay? So you can simulate it, or you can actually use Plex. I personally prefer this way because you get a better understanding about how the system is functioning, and you can actually be good at it. Once you do it a few times, you're going to be really, really quick at it. And again, remember I developed these models when Plex did not exist. So in case you end up working in a place that Plex doesn't exist, you can actually still run your system. All right, any questions? Yes.
So we write IC1 is IL2 minus IL1 into S3.
Okay.
So
the question is,
S3 get turned on together actually. So
what was the question?
okay, yeah, I guess.
You got it? You got it?
Yeah.
Okay. Any other questions? The overshoot, you mean the transient overshoot in the input voltage, in the output voltage? Yes, it goes to, okay, remember all power converters, power electronic converters have a transient kind of a behavior. Now, here I'm assuming that at the very beginning of the simulation, I'm applying duty cycles of 50% to the system. But in a real system, you don't have to do it. There is a mechanism which is called soft start, meaning that you start with a duty cycle of 2%, then gradually really increase it to 4%, 8%, then basically ramp it up all the way to 50%. Within I don't know, 5 milliseconds or something like that. If you do it that way, you can actually eliminate a lot of these transients.
Can we see if the resistance change, what happens?
Okay, we are curious about what happens if the load changes, right? So let's do that, assuming that I'm fast enough. All right, assuming that we have settled now, and I changed the load, so I made the load heavier in terms of the resistance is lower, so I'm actually consuming more power. We have a little bit of a transition over here, but still the output voltage is whatever it is, 70, whatever, 72 or whatever. And the currents should actually increase because now we are consuming more power. You can see the currents have increased a little bit. All right. Any other questions? All right. I'm going to post this simulation file on Blackboard in case you guys are interested in playing with. All right. So this was as long as this paper is concerned. So from now on, as a person who has been in this class, you should be able to analyze any of DC to DC converter that is placed in front of you. Don't get panicked if you don't know if there's a diode over there or if there's a switch. All you have to do is to identify the complementary switches, then basically make sure on average the voltage of your inductors should be 0. That's it. Very, very simple. All right, now we are going to move on to, okay, we are assuming that yes.
In all these example, 1 and 3 are active only, right?
What is that?
In this example, switch number 1 and 3 are active.
Right, right.
And not 2 and 3.
Not 2 and 4. Not 2 and 3, basically. Yes, that's right. So in the simulation that I showed you, S1 and S3 were the active switches. All right. So speaking of switches, now we want to see, if you really want to build this converter, what is the physical realization of this switch? Is this switch a diode? Is it a basically transistor? Is it a combination of a diode and a transistor? You know, things like that. So we are going to look at some of the physical switches that are out there. Before even doing that, let's talk about switches a little bit more. All right. So the first fundamental switch that you can ever find is a single pole, single throw switch. All right. So like a light switch, basically turn it on and off. There's one pole and one throw. So this is your switch. Your switch has a current of I. And again, passive sign convention is observed, a voltage of V. And also you have some sort of a control. Like your finger when you're turning the light on and off is the control basically. So control or command. All right, something like that. And please note that we don't really differentiate between this. As long as this class is concerned, these two switches are identical. It doesn't really matter how it is drawn, basically. It's the same thing. So we are assuming that these are identical. All right, so if you are curious about what kind of other switches do we have? Like for instance, we may have a switch like this. And they are controlled together. This is called double pole single throw switch. And then the one that we have seen already is single pole double throw switch. And we are going to get to this later, basically. Okay. So what do we mean by an ideal switch? Okay, an ideal single pole, single throw switch. C or command, sometimes they call it existence function. They show it with an H. It doesn't really matter. If C is 1 or true or for instance 5 volts, then switch is on. Okay, or it is conducting. Or it is eligible to conduct. Sometimes the switch is on, but it's not really conducting because, for instance, the current is flowing somewhere else. And we usually show it with a short circuit. All right. So that means the voltage drop across the switch, ideal switch, is 0. Doesn't matter how much current is passing through. So we don't really know how much current is passing through the switch. The rest of the system determines the amount of current. So we only know that the voltage of the switch is 0. And the other alternative is if the command is 0 or, for instance, false, or 0 Boolean 0 or 0 in terms of 0 volts, the switch is off or blocking. It is basically blocking the conduction of current. And it is like this, basically, like an open circuit, basically. Now, we don't know how much voltage appears across the terminals of the switch. The rest of the system determines that. All we know is that the current of the switch, ideal switch, is 0. All right? So if you look at the IV characteristic, you're dividing into 4 quadrants. 1, 2, 3, and 4. So ideally, our switch can have, for instance, conduct a positive current when it is on. It could be conducting a negative current when it is on. Or it could be blocking a positive voltage when it is off. Or it could be blocking a negative voltage when it is off. So we don't know. It depends on basically the system. For instance, if we have a switch that only conducts positive currents and blocks positive voltages, then we call it a single quadrant switch, or in this particular case, a first quadrant switch. Okay, single quadrant switch. Okay. Now remember, later on, sometimes you may think about taking your switch out, flipping it, and putting it back in. So basically, in that case, both currents and voltages are going to be reversed. Now remember that if our switch is an ideal switch, the multiplication of voltage and current is always 0. Either the voltage is 0 or the current is 0. So there is no power loss in our switch. So, however, if the switch is not ideal, then actually, in terms of the IV characteristic, we may be, for instance, if you're talking about the first quadrant switch, we may be actually somewhere off these axes, basically. So that means if you multiply the voltage and the current of the switch, then you get some number that is not 0. That means your switch is actually dissipating some power. Now, if you hear the term, let me just draw them here and actually then explain what they are. If your switch is supposed to conduct positive and negative currents, negative currents, but it is only required to block positive voltages, You're looking at a current bidirectional two-quadrant switch. For instance, a MOSFET is something like this. Basically, MOSFET can conduct in both polarities, basically both directions. Now, if your switch is only conducting positive currents, but it is required to block both positive and negative voltages, then we are looking at a voltage bidirectional switch. Okay, and we don't have an example for this, but you can actually add a bunch of switches next to each other to actually create something like this. For instance, one diode in series with an IGBT would do this. And sometimes your switch is supposed to be all over the place. It is supposed to be conducting positive currents, negative currents, positive voltages, blocking positive voltages, blocking negative voltages. So it's supposed to be a four-quadrant switch. And then later on you can see that for using, for instance, 4 diodes and 1 switch, you can actually build this switch, okay? So all of these switches have a physical realization in the world. All right, so we want to know, we have looked at a bunch of converters. We know sometimes the currents are positive, negative, voltages are positive, negative. And we want to see, in terms of the components that we have, semiconductor components that we have out there, which one of them would satisfy our need. So we have to look at look a little bit, not in depth, just a little bit at our semiconductor devices. So let's take a look at them. Semiconductor. All right. The first thing that comes in mind is a diode. Too much. Which is basically a simple PN junction. The voltage of the diode is always defined from its anode to its cathode, and the current is always flowing from anode to cathode. So by the way, this is anode. The P side of the junction is called the anode, and the other one is the cathode. All right? Okay. Now remember, diode is kind of an exception. It is a switch, but it doesn't have any control. We cannot command a diode to turn on and off. It actually makes its own decisions on its own. So they don't have a control input. And that is why they are called, they are still a switch, because sometimes they are on, sometimes they are off, but they are called passive switches. Okay, so in an ideal world, if we were able to find an ideal diode, the IV characteristic would look like this. So diodes, they can conduct positive currents and they can block negative voltages. All right, so here we call it that the diode is on or it is forward biased. And in this area we would call it off or it is blocking. Or it is reverse biased, basically. Okay, I think we are running out of time. I'm going to stop here. So after the diodes, we are going to introduce IGBTs and MOSFETs, and then we are going to actually see how we can use these components to realize the power electronic converters that we have seen so far. All right, so see you guys on Thursday. By the way, your homework assignment number 1 is posted, number 2 is posted on Blackboard.